Hey everyone! Today I wanted to share with you a very important electrical engineering signal processing concept that I feel like all EE majors should know. Even though this is a signal processing concept, it's an important concept even for people working in hardware. For instance, circuit design, analog to digital conversion, RF. And so I want to share with you this problem. Now this is a concept that you learn fairly early on in your electrical engineering signal processing intro courses, but it is such an important concept that I saw this problem again many years later during my Stanford PhD Quals. And so this is an important foundational concept. So I will start off by going over the problem and go over the procedure on how to find the solution, which is not obvious unless you've seen it before. And after presenting to you the solution, I'll explain to you qualitatively why this concept is important. And so without further ado, let's begin. So what is the problem? The problem is the following. What is the Fourier transform of an impulse train? So let's draw it out. So I just drew an impulse train where each impulse has an energy of 1, and the impulses appear every t interval. So just really quickly, let me explain to you what an impulse is. An impulse function is usually defined with a lowercase delta. This is a notation that I have an impulse that is centered at 0 with an energy of 1. And I use the term energy instead of magnitude, and I'll explain why later. So this is what the function looks like. So the way they describe an impulse to us in our introductory engineering courses that mathematicians really hate is to say that with this impulse function, it is a value of 0 everywhere, and at 0, it has a magnitude of infinite. So what do we mean by energy though? Well, what we mean by an energy of 1 is if we take delta t and we integrate across an infinitesimally small time interval around 0, we will get a value of 1. And this energy can be scaled to whatever value you like. It can be 2, 3, 10, whatever. And so if you think about it, the way I first described it to you about it being infinite at 0 and 0 everywhere else, it doesn't really make as much sense. And so that's one quick way to think about it. But another probably more official way to think about it is if I take the integral of delta t from negative infinity to t, I get the unit function. So it would look something like this. So this unit function can be denoted as u of t. And what we have here is it is 0 for all values of t. Let's assume the x-axis is t. So the way to define a unit function, u of t, is it is 0 for all t is less than 0, and it is 1 for all t is greater than equal to 0. So this is probably a more official way of giving you intuition and for you to understand what the impulse response, what the impulse is. I don't want to say impulse response because that's actually a different definition. So if I say impulse response by accident later on in this video, be careful, I probably made a mistake. So you'll notice that with this impulse function, delta t, I have an energy of 1. So if I take the integral from negative infinity to t over this function, I will get a value of 0, and then bam, a step function to a value of 1. And if I scale this impulse response to another value, say 3, then this step response will step up to a value of 3, and so on and so forth. So this is kind of a longer, more thorough way to explain the impulse. And sorry if you already know about this, but just wanted to give some background. So let's move on back to the question. So here I have my train of impulses again, and they are scaled. Each impulse is scaled with an energy of 1, and they're shifted t apart. It's a periodic function. So 0, t, 2t. All right, and as I was explaining the notation earlier, you can explain it as a sum of shifted impulses separated by t. So how do we go about solving for the Fourier transform of this periodic function? So what's the definition of a Fourier transform? The definition is the following. Now there's lots of notations out there for the Fourier transform depending on what textbook you use, who your instructor is, etc., etc. You could have an omega, you could have a 2 pi f, it could be in terms of f instead. There could be some scaling factor, but I will stick with one notation to be consistent, specifically from the Oppenheim and Schaefer textbook. So this is the definition of Fourier transform using this particular notation. If you were probably starting out learning about Fourier transform, the first thing that you would think to do in finding the Fourier transform of this impulse response is to do a substitution, because the Fourier transform is this function as a function of f of t. So what happens if we substitute here into here? We will get the following. So in this result, I basically get a summation of exponentials, sinusoids. Now, nothing we've done here is incorrect. In fact, every step here we've done is sound. We sort of have to interchange the summation and the integral, and then we get this final result. However, this result, though correct, doesn't really give us any intuitive understanding on what the Fourier transform of this impulse response is. So it's not obvious how to plot this or graph this. So this is actually not a very helpful solution, even though the steps that we've taken are correct. So if people were to ask you what the answer is of this is not exactly the answer you would be looking for, because it's not helpful. So what is the better approach that we should take when solving this question? Okay, let's start over. So in order to solve this problem, you actually need to know a certain trick, and that involves the use of the Fourier series. So, earlier I just mentioned the Fourier transform. Now I'm talking about the Fourier series, which is, it's different. Okay, and later on down the line, we have to be very careful listening to me talk, because when I say Fourier transform, Fourier series, one is not the other. So what's the difference between the two? So the Fourier series and the Fourier transform are very similar concepts with slight differences. For instance, the Fourier series applies specifically to periodic functions, and it decomposes a function into a discrete sum of sinusoidal components. The Fourier transform, on the other hand, which works both on periodic and non-periodic signals, it will convert this time domain signal into a continuous space of its frequency components. And so you might think, well, they're basically the same thing, and in some sense they are. Both the Fourier transform and the Fourier series converts time domain signals into a different modality that exists in the frequency domain. Okay, so now let's get to solving the problem. To start off, let's consider the following. Let's say we are in the frequency domain and we have an impulse that is located at omega naught, scaled by 2 pi. Let's draw it out. I'm going to write out the equation real quick. Now you might ask, why do I have to scale by 2 pi? Well, it turns out it'll make the math work out a little easier later on. You'll see its importance. So this is the equation, fairly simple. It's just an impulse response, scaled impulse response, located at omega naught in the frequency domain. Now, what is the signal in the time domain? If we converted it from frequency to time domain, what is the equation going to look like? Well, let's work it out. First of all, the equation for the inverse Fourier transform, using our notation. This is the equation for the inverse Fourier transform. Now what happens if I substitute this into this equation to find the signal in the time domain? It will look like the following. So now you know why I have the 2 pi in there. It's so that it cancels out the 1 over 2 pi in the equation we have for the inverse Fourier transform. And so I get the following for the time domain signal. If I have an impulse response shifted at omega naught, scaled by 2 pi, and convert that to the time domain, I actually get e to the I omega naught t. Let me clean this up and write it so it's a little more clear. I just summarized the result right here. Inverse Fourier transform of this impulse is this exponential. Now that we have this, consider the next scenario. Let's say in the frequency domain, I have the sum of a bunch of impulses separated by omega naught, with each impulse scaled to its own value. What is that going to look like from an equation standpoint? Let's write it out. So I have here a summation of impulses separated by omega naught, each scaled with a value of 2 pi a of k. We decided to denote this coefficient a of k, and I decided to add in this 2 pi without loss of generality. The 2 pi will make the math down the line easier, just like earlier. But there's nothing wrong with adding this 2 pi because it would simply take whatever coefficient we would have had and divided that by 2 pi. Now that we have this function here in the frequency domain, what is its inverse Fourier transform? What happens if we convert this frequency domain function, into the time domain? Well, we can do a similar thing. We already have the simpler case up here. It would simply be a bunch of summed, scaled exponentials. Let's crank it out. Again, we see that the 2 pi's cancel out up here, which you'll understand is why I decided to add in that 2 pi there. And we're actually given a result that's not surprising since we already did the simpler case up here. The inverse Fourier transform of a sum of these scaled impulses is equal to sum of scaled exponentials. And we have basically summation of k, a of k, e to the I k omega naught t. So looking at this result, it's pretty much what we expected. We didn't necessarily need to go through this whole derivation, but we want to be thorough. So let's rewrite the board just to make it a little cleaner. So now here we have the result here for you to see. Now we're going to do something very interesting where we're going to substitute omega naught for 2 pi of t. So this will equal the following. So we did all of this simply using Fourier transform. But if you look at this result here, after substituting omega naught for 2 pi of t, this looks a lot like the equation for a Fourier series. So Fourier series is for periodic functions, right? But we got these equations. We went through this math using only the concept of the Fourier transform. So now it's starting to get kind of interesting here. With this result, we're going to take another path right now. And we're going to look at the definition of a Fourier series. Okay? Now let's go back to our original function, f of t here. We have a summation of impulses that are separated by a period of capital T. If we wanted to look at the Fourier series of this, what would it look like? Well, let's go to the definition of a Fourier series. So let's divide up the board. The equation for a Fourier series is the following. I'm going to denote the Fourier coefficients b of k. So this is an equation for deriving the coefficients of a Fourier series. And remember, Fourier series are primarily targeted for periodic functions. So we're actually going to write out the equation and find the Fourier coefficients for this function, assuming that the period is capital T. And so let's substitute this equation here and derive the coefficients. So we have something very interesting here from observing, in that we realize that in this summation, the only non-zero term that exists is when k is equal to 0. So that simplifies this expression here. Sorry, I forgot all the negatives. So we find that if we solve for the Fourier series coefficients, from all this math, we see that when we're solving for the Fourier series coefficients for this function here, we actually get that each coefficient value is 1 over t. So if we write out the function f of t as a sum as a Fourier series, we get the following expression. Now, having taken f of t and writing it as a Fourier series, look at this expression here. What does it look like to you? Now, I haven't substituted b of k in, but b of k would be 1 over t for each of the values as we solved here. So looking at this result here, we actually see that we can pattern match these two. This expression here looks exactly the same as this expression here, except we wrote down this expression as the Fourier series of f of t. This expression here is equal to f of t. right? But now we see that here, which pattern matches to this expression here, is the inverse Fourier transform of this expression. Which means that if we can match these two to be equal, the Fourier transform of this expression f of t is equal to this here. This summation of scaled shifted impulses. So we basically have solved the Fourier transform of f of t. So the Fourier transform of a sum of shifted impulses is also a sum of shifted impulses, right? Of course, each of them are scaled. So in this case, all we have to do is match a of k with 1 over t. So the Fourier transform of f of t is equal to this expression, where a of k is 1 over t, and omega naught is equal to 2 pi over t. So this is our Fourier transform. Ta-da, we have the answer. So the Fourier transform of a sum of shifted impulses is also a sum of scaled shifted impulses. Make sense? Let's quickly summarize what we did in order to solve for the Fourier transform of this impulse train. What we had to do is, in the beginning, when we considered the following, we basically made a guess as to what the Fourier transform of that function could be. And later, by taking advantage of the fact that the impulse train is a periodic function, we looked at its Fourier series, and we used the Fourier series to prove to us that this Fourier transform is correct, and also to help us calculate what the coefficients a of k would be. And that allowed us to arrive at the final solution, the Fourier transform of this f of t. This is honestly quite cool, and it might take a few times of going through this in order to really understand what was done, because it does put many different concepts together. Now, this is a very important result in signal processing, but especially in hardware and analog to digital conversion, which is in everything. Without getting involved in too much math, let's just qualitatively talk about why this result here that we just arrived is important, because that's the whole point here. Okay, so the Fourier transform of an impulse train is another impulse train. To qualitatively describe this significance, we're going to avoid talking about the scaling factor for now, okay? We're going to focus solely on the distance between the pulses, okay, the impulses. So here we notice that capital T, which is the period of the impulses in the time domain, is actually in the denominator here in the frequency domain, which means that qualitatively speaking, if I had an impulse train, in the time domain, if the distance between my impulses in the time domain becomes larger, that means that in the frequency domain of the Fourier transform, the impulses will become closer together. On the other hand, if in the time domain the impulses become closer together, then in the frequency domain, the distance between the impulses will become further apart. There's an inverse relationship between the distances between the impulses in the time domain and the distances between the impulses in the frequency domain. So why is this important? Well, if I had a function that is being sampled, okay? Let's say I have some random function x of t. If we're sampling x of t in the time domain, we're basically multiplying it by an impulse train. I'm going to denote the impulse train by this function. Okay? This is common to see. So just to make the notation easier. So whatever function I have, I'm basically multiplying it by this impulse train. Makes sense, right? Because you're taking samples here at every time interval. Now, what is happening in the frequency domain when I multiply by an impulse train? It turns out if you take a Fourier transform of this expression, then what you have is you have the multiplication becomes a convolution, and you have the convolution between the frequency domain signal of x of t and the frequency domain signal of your impulse train, which is another impulse train. In the frequency domain, it would look like this. This is x of omega, but this is not literal. This is just a representation of what my Fourier transform of x of t is. And I'm convolving it, that's the correct term, convolving it with the Fourier transform of this impulse train. So this is what's happening in the frequency domain. A sampling operation results in a convolution in the frequency domain. Now, what does this mean when I'm taking this function and convolving it to an impulse train? Well, it would simply be taking this function, because x of t is a real function, this is actually Hermitian symmetric, but don't worry about that result for now. This is something you can prove later on. But the point here is that in the frequency domain, I have x of omega being convolved with an impulse train, which will look like this. But you'll see something interesting. I assumed that 2 pi over t is greater than the width, what we call the bandwidth of this signal. When you sample a signal in the time domain, you are basically replicating the signal in the frequency domain. But now you see an interesting problem. If your impulses are too far apart with one another, it causes the impulse function in the frequency domain, it causes the impulses in the frequency domain to become too close together. And this causes this signal to overlap with itself during this replication process. So the signal overlaps with itself, which is what we call aliasing. And this can be bad. If you have too much aliasing, it can cause your signal to overlap and corruption in your data. There are different ways to solve that. One would be to sample faster, to bring these impulses closer together, and thereby bringing the impulses in the frequency domain further apart from each other, and so you don't get this overlap. Another way to solve this is to provide an anti-aliasing filter, in which case you cut the signal at the ends so that they don't overlap with one another and corrupt itself. And so that is the significance of this result here, okay? So that you can understand the effects of sampling your signal in the time domain. We're out of time. I hope this derivation was cool to see. It's a very important result and with a very important implication. So I hope you learned something today. I hope this was enjoyable, and have a nice day.